Hey team, I'm Maddie. Welcome to ScienceSideUp. And today we're going to talk to another good friend of mine, Linda. I know Linda from college, and she is a civil engineer who studies Roman concrete. And you'll notice I am filming from my living room instead of my normal space. That's because my internet router is right there. Zoom meetings, as I've learned in quarantine, go much better when I am close to my router. So, lessons. Okay, Linda, so can you tell us a little bit about what you do and sort of the journey of Linda, of how you sort of got into the field you're in?
All right. So currently I am a fourth year PhD student in MIT's Department of Civil and Environmental Engineering, and I study something that we call antiquity-inspired construction materials.
Could you give me the 30-second version of your entire dissertation?
Yeah, okay. Two major differences between modern concrete and ancient concrete. So the biggest difference is the raw materials and what we consider the different types of concrete. So we consider Roman concrete what we call a hydraulic lime mortar or concrete. And what this means is limestone is the primary component. You heat it up in order to drive off the carbon dioxide and make it reactive. You add in some sort of aluminosilicate source, and these two, in the presence of water, react. It allows it to set underwater, but because the lime is the main component, it makes it a little more ductile. It makes it a lot more porous. It makes it less strong than our modern concrete. Modern concrete, on the other hand, is also a hydraulic mortar. We don't call it a hydraulic lime, though. The way modern cement is made is you take clay and you calcine it at, what's the temperature, like 2,700 degrees Fahrenheit? It's like 1,400 degrees Celsius.
Mm-hmm.
So really high temperatures compared to what you need in order to make Roman concrete, which requires temperatures of like 900 degrees C. And you heat that up and you add a little bit of limestone to it, but you also add different things like gypsum and all sorts of stuff into it, and you produce what's called clinker. And this clinker is ground up really finely, and that's the powder that ends up reacting. So like modern cement is kind of an all-in-one thing. You get the gray powder, you add water, boom, you're gonna have something that's hard. Roman concrete, on the other hand, is a little more hodgepodge.
So just for the non-scientists in the audience, you said that Roman concrete is a little more ductile, which makes it less strong. So we're talking about forms of deformation, right? Roman concrete, as compared to modern concrete, is more apt to maybe bend a little bit. And that's the balancing act between strength and brittleness. Right.
Yeah, Roman concrete, the way that it is, it has a lot more, essentially little air bubbles in it, right? A lot more holes. Okay. And these holes, kind of like a sponge, make it a little more squishy than modern cement. So modern cement also has lots of little holes in it, but they're at a much finer scale, and they're a little bit different than Roman concrete. And modern concrete is going to be much more stiff. It's going to be more dense, and that kind of thing.
Okay, so earlier when I was saying it's up to bend, I was doing the wrong way. It's not gonna bend; it's gonna squish.
Yeah, it's more of a squish.
Do you think that squishy aspect of it can lend itself to durability? Just thinking on, like, it might not be able to hold as much weight as modern concrete, but this concrete is more able to sort of adapt to its environment. So anybody that's ever laid a driveway or a sidewalk and has a tree in their yard, right, knows that within 10 years, you're going to get that root popping up and breaking your concrete. So our concrete isn't really designed to give or adapt. It's supposed to be a very strong material. Am I speaking nonsense, or?
No, I think that covers it. Yeah, one of the great things about lime-based mortars and concretes is because they have this ductility, that ability to move a little, it makes them apt for different types of masonry structures. It makes them apt to survive in various climate and seismic zones, right? So there are Roman structures that have survived earthquakes, and it's interesting because there's some conservation issues where structures have stood for centuries through earthquakes, through all sorts of crap, and then the engineer comes in and is like, well, this isn't like according to modern code, therefore it's unsafe, and they add these like steel reinforcement bars, or they try and like shore it up. Next earthquake comes, boom, it's down, because it adds this lack of ability to move. So I deal with structures that are on land, but one of the people that I work with, she deals also with structures that are underwater, ancient structures that are underwater. And one of the really cool things about the underwater structures that she studies, so things like harbors, the Roman concrete, so modern concrete, it does its thing, it cures, it hardens, and it reaches a plateau where it's kind of gaining more strength over time, but it's negligible, essentially. Roman concrete, on the other hand, with all of these little pores, all of these little air bubbles in it, essentially, has the fluid interaction with the water, with the marine environment. And there's all of these processes going on that cause further crystallization, further minerals to form in these little holes to like make it strengthen over time. So over the 2 millennia that it's been in this harbor, it's continued to be a living structure in a way. It's continued to grow different minerals that help it survive. And so this is also something that's really interesting that we haven't necessarily seen as much in the aerial structures or the ones on land that I study. But who knows what we'll find with the aqueducts.
So one of the things that I study with ancient Roman concrete is the fact that they would actually take rubble, old pots, all sorts of stuff, and crush it up and put it in their concrete. So that way they weren't really wasting anything that was no longer usable, for example. And they were giving it the second life, and they were doing it in ways that actually added additional strength to their structures. And they would design some of their structures in order to be used for multiple generations or in multiple ways. And this is something that's been done kind of throughout history that we've kind of lost sight of in building things fast and building things quick and building them for one purpose. And so kind of designing with this idea of reusability in mind can help us reduce that amount of reconstruction that we're doing, reduce material use over time, and in turn impact sustainability.
Somehow they were able to make concrete with an inconsistent recipe that's still consistent in its results.
Yeah, so actually, fun fact, one thing that I recently learned was the shipping routes that the Romans had throughout the Mediterranean. They would take, bread and grains from Egypt and these places and try and bring it back to Rome. And in order to not send the ships back empty, they would actually fill them with pozzolana, which is one of the ingredients in concrete, essentially. So that way they could get rid of all of this sand, essentially, use it to build stuff at other parts of their empire, and these like grain shipping boats didn't have to go back empty. So they did have ways of transporting some of the raw materials, but you're right. One of the great things is that they used local materials, and wherever possible, they tried to find suitable replacements for things that they didn't have. So the Romans are famous for iterating upon the concretes and mortars that had existed previously by adding volcanic ashes and sands in order to make something that could set underwater, which was really great for harbors, really great for durability. But volcanic ash it's hard to find in some places, right? And so they actually had a set of criteria that you could use in order to understand what things you might be able to add in place of that. Potsherds being one thing. So if you don't have volcanic sand, some of the ancient historians say, crush up some pottery and put it in, and this will act as a substitute. They had really strict specifications for things like the limestone that they would use in their concrete. So they would say, stake out the limestone that is the purest of white, so it lacks impurities, and with this you'll have the best concrete. I actually have something I can show you.
Okay, great.
So this is a really old book. This one's not ancient. How good is your French?
Not.
So it's Vitruvius, and it's his 10 books of architecture. Yeah. And Pliny the Elder is another one that gives us a lot of good information about concrete. His recipes and his teachings of architecture are something that were passed down for many generations and have been intriguing to historians for a very long time. That we're able to document these different kinds of recipes that you could use and different things that you could look for when trying to find substitutes in order to build your roads or your houses or something.
And my journey to get to this point where I get to look at old concrete every day, it's a little like, I don't know, not straightforward. So I grew up on a chicken farm on the eastern shore of Maryland. I was checking the mail at the end of the lane that our farm was on. And one of our kind of down the street neighbors was walking his dog, and he ran into me and he was like asking me, this was my senior year, and he was asking me kind of what I wanted to do. And I was like, well, I really like building stuff and I really like bridges, so I think I'm going to go into engineering. He's like, oh yeah, I heard that you were interested in engineering. And he was like, so there's this guy in my church that went to MIT, and he wants someone from the eastern shore of Maryland to go to MIT, and we think you'd be a great candidate to apply to MIT, so you should apply to MIT. And he has a scholarship fund there, so like, you know, they're really good with need-based aid and that kind of stuff, so we think that like it would be affordable for you and your family, and so you should apply. Fast forward to Pi Day 2010, and our family's like sitting around the table eating a giant pile of steamed crabs, and I'm like, oh, it's time to check to see whether I got in. And then I got in, and that was really weird. So then I went to MIT, and that's kind of how I ended up going to MIT, and I was able to like study civil engineering. And in addition to loving bridges, I learned that I really love concrete. So recently on my Facebook memories, there's a picture of me on a school trip in undergrad, and I'm just like stroking the concrete of a building. And so clearly this is something that I've loved for a really long time. But being a first generation student, I also like wasn't that sure what exactly graduate school was for in the long run. So I didn't know what kind of degree I would want to get. And I knew that I had student loans, and I was like, oh, I should pay off student loans. So I took a job that would give me both engineering and project management experience to try and figure out kind of what I wanted to do within this world of civil engineering that I had come to love. And during that time, I learned that I really liked the technical aspects, and I really struggled to understand why we only design buildings to last for such short periods of time when we don't design them to be used to their fullest extent, when they're always falling apart after only 10 years. It just didn't seem very sustainable to me that we kept on tearing things down after only a few decades, when things can be reused and we can build more sustainably. And so I applied to grad school with this concept of durable engineering in mind, durable and sustainable. And that's when I met my current advisor. And he likes espresso, I like espresso. Here we are now.
You apply to the PhD program, and your interest is predominantly like, so you said like the technical aspects. So like, what are we making things out of, right?
Yeah.
Okay. And then broadly your advisor, do they only do Roman concrete, or do they have broader interests?
Much broader.
Okay.
So Roman concrete is the thing that we kind of share, that we talked about kind of when I did my interview. But he has followed two paths. He's followed this path of like ancient stuff. So he did his PhD on the Dead Sea Scrolls and like the preservation of parchments. Really interesting stuff.
Okay.
And he's worked on like preservation projects and conservation projects such as Bernini's colonnade around St. Peter's Square in the Vatican City. So he's like become a big shot in that area, but he shifted at some point and he went towards like bio-inspired engineering and worked with the Max Planck Institute in Germany for several years before coming to MIT. So now he's using his lab at MIT to pursue both of these interests simultaneously, essentially. And basically taking this bio-inspired approach and his like history and archaeology stuff and using the bio-inspired approach with this archaeology.
That's really cool. So to me, it sounds like you sort of exist in this very interesting intersection of civil engineering and like material science and archaeology. And I was wondering if you had thoughts on kind of, there can't be that many people in that intersection with you. Is that
right?
Okay.
But one of the great things about being in this intersection is that I get to work with people from all sorts of different fields, right? So you pretty much hit the nail on the head in terms of the three areas that I work in. But I work with people who are conservators, people who have studied chemistry and are applying it to like ancient materials. I work with material scientists, of course, and civil engineers because concrete and bridges are awesome. But what's great is that I feel like there's so few ways in which we can have truly interdisciplinary conversations in science and engineering, because I feel like a lot of times people get kind of siloed and they get very interested in what they're doing and kind of put their blinders up in order to move forward, which is important, and really great things come out of that. But what I love is having that conversation where in the room you've got people from 5 very different backgrounds, 5 very different fields, and you're all working to solve the same problem of trying to understand what's going on with a particular piece of architecture or a particular pigment or something. I mean, I'm working with people who are geologists also. I'm working with people who study like classics.
Okay.
So in addition to studying Roman concrete, sometimes I study ancient Egyptian pigments and get face to face with old sarcophagi.
That is so cool.
One of the things that I study, so in this realm of antiquity inspired materials, we don't just do it for construction materials. We also look at things like Egyptian blue, which is in one of the first or the first synthetic pigment that we know of. So it's the first thing that humans made as a pigment. And it has this really cool property where it's basically this nanosheet structure. And when you shine visible light on it, so just like an LED light on it, it actually then emits light in the infrared range. So you can pick it up with an infrared camera just by shining a visible light on it. So you can distinguish it from different other pigments. And it has like applications in all sorts of things like biomedical imaging and solar arrays and all sorts of cool stuff, even though it's like this 1,000-year-old technology. So here we're just using like a standard digital camera that we've taken a filter out of, so you can see the infrared light with it, and we shine stuff in museums with this LED light and are able to pick it up. And so things like the headdresses on sarcophagi and whatnot tend to show really bright in infrared because they're just slathered with Egyptian blue, even though it no longer looks blue.
That is so cool. That's really
so I have some pictures that I can show you. I made a PowerPoint.
Yes.
Okay, so I'm going to tell you the story of the aqueducts and how I work with this person who's like reconstructing the climate of ancient Rome, but I'm studying the mortars and how it comes together in like a super cool way.
This is really awesome.
I'm like, I love telling this story. This happened just last summer, and it's like, it reignited my passion for the subject. So this is me, and we're in Tivoli, Italy. So it's just outside of Rome. It's really cool because as you're taking the train into Tivoli, you go over this bridge and there's this waterfall on one side. And if you look out onto the other side, you just see like one of the old temples of Apollo from like the ancient Roman era. You're like going around the bend and whatnot in order to get there. It's like super cool. So we come to Tivoli, and what we're studying is this aqueduct right here. So this is the Anio Novus, and it supplied water to ancient Rome from some springs up in the Apennines, I believe. Aqueducts are really cool because they were designed in many different ways. Sometimes they were above ground, sometimes they were underground, sometimes they were level with the ground. And up here actually is right where the water would be flowing. So this is probably about 6 feet tall. And in some cases, when aqueducts were joining together as they were entering the city, they would be stacked right one on top of the other with these water channels. And there's this plaster layer on the aqueducts, and it goes about halfway up the side, and that's where the water level would have been. And I'm really interested in these plaster and mortar layers, right, that would have been in contact with the water because they had water flowing over them continuously. In some cases, they were used for centuries beyond the Roman Empire, right? And they are still there today. So this is something that's really interesting, but this is also very high up in the air, so I can't get to this particular channel, and it was really sad. This picture over here, though, is me right when we had just found where the channel had come out of the ground. So we followed the trajectory of the aqueduct going back this direction, and we were able to find it. So we dug or cleaned off the top a little bit to get rid of some of the vegetation, and you can see the aqueduct right here. So this is basically hard water buildup on top of the aqueduct. So it was actually there were some Romans whose job it was to go into aqueduct channels. They were built with little manholes in them, so that way people could get in and actually chisel this hard water buildup off occasionally. Of course, when the empire started to fall, things were going into disrepair. This didn't happen as often, and so this hard water buildup is really common in the ancient aqueducts that we study today. So this is actually indicative of certain things of the climate because of the carbon dioxide that gets stored in the calcium carbonate buildup. It's really cool, and also these like ripples on it can tell you about the water flow in the channels at the time that this deposit was made. So these are the kinds of questions that that Duncan is studying, and it's really interesting stuff. And it's right on top of this plaster layer, which you can see here. And then that plaster layer is on top of kind of a chunkier mortar concrete. And these red bits in the concrete, that's part of the recycled aggregate that I'm interested in understanding how it plays a role in the durability and whatnot. So we were able to take samples from here, which is really exciting.
That's awesome. So those red bits, is that like the broken pottery things that you were talking about earlier?
Exactly. Okay. So that's broken up, basically terracotta pots, essentially.
Okay.
In some cases, they might use bricks from old constructions as part of their aggregate as well. And so when I talk about aggregate, what I'm talking about are the rocks and sand and the chunky bits in a concrete. So a concrete, when you're like walking on the sidewalk, there's like the gray stuff and then there's the rocks. So the gray stuff is cement, and then the rocks and stuff are the aggregate.
So this is me using the X-ray, portable X-ray fluorescence at an archaeological site in Israel. So yeah, I really do get to meet patrons. It was super
That's
exciting.
awesome. So how many places have you gotten to go to do civil engineering archaeology?
So most typically I go to Italy every summer. I've been to Israel to do the archaeology part. I've done, so there's this one like gathering of scientific methods and cultural heritage that gets together that took me to Spain, which is really great. And then of course, whenever I'm doing these things, I always try and do a little bit of personal travel afterwards. And so as a result of going to these places, I've also been able to go to places like Portugal, where I went wine tasting in an aqueduct, would recommend. And I've been to like the Netherlands and also.
I took an entire year-long class learning how to study potsherds so I could apply it to my mortars essentially. So I like wrote a paper on cooking pots, even though like my long-term goal was writing about mortars. So
That's amazing.
Yeah. So this is the sample that we were able to take, and this is like the buildup. Here's that like thinner plaster layer, and then like the chunkier concrete underneath.
Okay.
Okay, so here's where I get to talk about how I then take them back to the lab and I destroy the samples. Not really. I cut them into thin slices, and I study them with a variety of microscopes. So we get them thin enough, and this is one of the ways that archaeologists study ceramics in general, is and geologists study rocks this way. You cut a thin slice of the of your sample so thin that light can transmit through it, and then the way that the light transmits through the sample tells you different things about the minerals that are in it. In the case of ceramics, it can tell you things about their production. In the case of mortars, it can tell you about the type of mortar that it might have been, and how it might be degrading over time. So there's a lot that you can learn. So in this case, the light would be coming from the bottom here, shooting up through my sample and into the lens that I would then look through in order to see these types of features. And the stage gets to rotate, so you get to make your sample dance, which is a lot of fun. Another way that I might study my sample after I slice it in a slightly thicker way is with a laser. So this is called a Raman microscope, what I'm using here. And what I'm doing is I'm taking the laser and I'm shooting it down into the sample, and the laser excites the molecules in the sample, because who doesn't like dancing at a laser show, essentially? So the molecules do different things like stretching, vibrating, rocking, twisting, all sorts of things, and I can capture these phenomena and use it to fingerprint different mineral structures that are in my sample. And I can do this in different ways than the previous method, so ways that are both complementary and tell me both similar and different information. And then the last thing I might do with my sample is put it into the scanning electron microscope. So in this case, it's like it's in a vacuum, so I can't take my camera and take a picture of it in the microscope while the microscope's doing its thing.
Right.
So when I use the scanning electron microscope, now I'm interested in seeing what the elemental information is, and what the structure of the sample looks like at really high magnifications. So micrometer level scale, what's going on in my sample. So it's really exciting.
That's really cool. You have so many cool toys.
Oh my goodness, the toys are amazing.
This is super cool, Maddie. This is like the conservation center at Pompeii, which isn't open to the public. So with this cool research, we get to go to really cool places that like other people don't get to go. Oh my goodness, it's so much fun. Everybody should be in civil engineering Indiana Jones, because you get to see really cool things. So these are like little terracotta things, those pigments that they found throughout Pompeii. And then here are various carbonized remains of food. that they found when they excavated it. And my favorite part was this loaf of bread where you can see the fingerprints from the person, from the baker or person that had it prior to Mount Vesuvius' eruption.
Wow. I had a question, but I'm super distracted by your Pompeii backstage pass.
Some of the aqueduct samples that we're studying go into Pompeii, and then we have some from like the cisterns and pools and stuff there. So stay tuned for information on their water infrastructure.
Say hi, Tony. Bye. Say thanks for joining us, everybody. Like and subscribe.